Okay, guys, we're just going to do a quick intro to Unit 2. Um, you have finished the Unit 1 exam by now. Big sigh of relief. Hopefully, it went well. Unit 2 is going to be very different than Unit 1. We're going to start off today by talking about something you're pretty familiar with, which is correlation. And so, we're going to have two variables today, and we're going to talk about how they might be related to one another. You're familiar with the concept. Height and weight definitely have a relationship to each other. Height and age up to a certain point have a relationship to each other, and then you start not getting taller anymore. Lots and lots of things can be related to each other, and we're going to talk about those relationships today. So, one thing you've been confused about your whole life is what correlation actually means. Um, so you'll hear people on TV or on in the hallway talk about two things being correlated, and they don't really mean that. And so, one thing we want to be very clear about is that correlation has to be a linear relationship between two quantitative variables. Quantitative. So, like, you would never hear anybody correctly say hair color is correlated to SAT scores or something like that, because hair color is not quantitative. So, very, very important that you only use quantitative variables and talk about a linear relationship. There's other kinds of relationships, right? Quadratic relationships and all kinds of other types, exponential relationships. But we're talking linear between two quantitative variables. So that's really important. Let's start with that. You have your notes out, hopefully, in front of you. I'm going to share them. Let's share this. Here we go. Okay, so the first thing is our definition: strength of the linear association between two quantitative variables. Before we start talking about correlation, much like almost everything we're going to do this year, we're going to check some conditions and make sure they're met before we start talking about correlation. And so we already talked about two of these. One's the quantitative variables condition. So don't talk about correlation unless your variables are quantitative. Two is the straight enough condition. And so all that's going to mean is when you make a scatter plot of your x's and your y's, whatever they are, the dots kind of make something that looks linear, straight enough, and it's a judgment call. You don't want to have a lot of curve in it. You can have some dots that aren't on a best fit line or whatever you may call it, but you don't want to have any curve really. And number three, no outliers condition. If we try to make a scatter plot and we have outliers, we're gonna struggle. So those are our three conditions. Want to always check them before we proceed with a correlation problem. So start us off. This is an old example from actually from the first year of AP Stats, and it really happened. And I liked it so much that I kept it in the notes. And so here's what it says. This was a true story. On Saturday, I was eating lunch at Steak and Shake in Effingham, Illinois. I was on my way from a soccer game in Champaign where my son and some other people were playing. I was on my way from Champaign to St. Louis to sit in a beautiful suite at a Cardinals game, and I was with some other people, and someone also with me, somebody else eating lunch, mentioned he thought there was a correlation between items on the menu being pictured and being bought more than average. So, like, Steak and Shake, the menu's got some pictures of good looking food. And he said, I bet, you know what? I bet people buy the ones that are in the pictures more. I bet there's a correlation. He used the word correlation. It was really kind of freaky because we were about to start the unit and he was in my class. Well, first of all, do you believe on average people buy items that are pictured on a menu more than those that aren't? Probably the answer is yes, they do. I wonder if being pictured on the menu causes them to be bought more often, or if being bought more often causes Steak and Shake to picture them on the menu. So I'm leery about any type of using the word cause or causation. But I'm also very leery about using the word correlation here because, as you just learned, correlation has to be between two quantitative variables, and being pictured on a menu is not quantitative. So there might be a relationship. You might say there's an association between being pictured on a menu and being purchased more often, but there darn sure heck isn't a correlation. And so that's an easy example, but it was too perfect. And so I had to leave it in the notes. Okay, here is a real correlation problem. So example 2 says below are heights and weights for the dudes in AP stats. I made these up. They're not real. Don't be offended if you're smaller or bigger or not in here, or if you're a female, don't be offended. Comment on the strength of the linear relationship between the two variables. So what we're going to do every time we're presented with a data set like this, is we're going to put it in the calculator, and we're going to have the calculator do some work for us. So, luckily for you, I've already put this sucker in the calculator. So let me bring up my calculator. Boom, there it is. So first dude is 67 inches tall. That's 5'7", weighs 140, blah, blah, blah. I put all 25 in there. This is going to be our first problem we've done where we have two variables. Everything in unit 1 was single variable, and now we have two. So when we go to do a calculation here, watch the steps carefully. We're going to still hit menu. We still like statistics. We still like calculations. We got two variables now. So let's pick two variable statistics. And then your calculator is going to say, what are they? The first one I called height, pick it. Second one I called weight, pick it. Where am I going to put my results? How about column D? I like to leave a blank column. You know that about me. I don't like to crowd stuff in. So let's go ahead and do it. We're going to get some results on here. I'm moving my picture around. So the neat thing about these results is now we have all kinds of information, lots and lots of information. We have this thing, X bar, which of course is the average height. So the average male in my AP Stats class is 70.96 inches, which is just shy of 5'11". We have the deviation, which is 2.17, give or take. We can certainly draw a normalish curve and label it and hope that it was pretty accurate. But we have more below this. We have, well, 25 is the number. We have, look at this, we got Y bar. We got a new variable with a bar over it. And of course, that means average, and Y is my weight. So the average weight is 153.6. I bet we have a deviation. Look, it's S sub Y. Remember, that's a sub Y. Your calculator's bad at that. And that's 21.05. So the typical kid, a male in my class, weighs 153.6 with a deviation of 21. We could draw that curve. But here is what we are interested in this unit. We want to know, of course, how do those two relate to each other? Well, we haven't had a chance in class to talk yet about correlation, but I think you can imagine if the weight goes up exactly predictably based on the height, that'd be a perfect correlation. So if somebody is an inch taller than somebody else and they weigh 10 pounds more every time, that'd be a perfect correlation. Well, that's not really what happens, right? There's plenty of tall people that don't weigh as much as not tall people. But in general, tall people tend to weigh more. There's a big important word we're going to use a lot. Tend to weigh more. And so there's some kind of a relationship for sure. If there were no relationship between height and weight, we would have no correlation at all. As a matter of fact, there's a number that we would associate with that. It'd be called 0. If there were no relationship between height and weight, we would say the correlation is 0. Think about this. If the taller people always weighed less, they'd be funny looking, and that would be a weird correlation. That'd be a backwards and negative correlation. So we can have positive correlations, we can have negative correlations, and of course we can have no correlation. The perfect correlation has a number associated with it, and it's 1. So, if I measured all of you guys in inches and measured your height, and then I measured you in centimeters, I promise you there would be a perfect correlation between your height in inches and your height in centimeters. There would be a 1.0 correlation. And correlation is so special it gets its own letter, and it's going to be dun dun dun. It's going to be R. So R is going to stand for, write this down. R is going to stand for the correlation coefficient. Correlation coefficient. Look at this one, 0.75. That's not too far away from 1. So that's going to mean, in general, as heights increase, weights tend to increase for males in my AP Stats classes. Pretty close to 1, actually. 0.75 is a pretty solid correlation. When we talk about correlation, we're always going to talk about the strength of it. And there's no hard and fast rule. It's not like 0.75 is moderately strong or pretty gosh darn strong or really strong. It depends on the situation. In this particular case, we're talking about heights and weights. I think that decimal is pretty high. I'm going to say there's a pretty gosh darn good correlation between height and weight, using my own words. I'm also going to call it linear, but not until I look at the graph, but I'm pretty sure it's going to be linear. So I'm going to talk about strength. I'm going to talk about form, that's linear. And I'm going to talk about direction, that's positive. So strength, form, direction, strength, form, direction, strength, form, direction. Just like when we talked about a histogram, we talked about shape, center, spread, shape, center, spread. Well, here we got 3 things we're going to talk about also. Okay, let's look at the picture. So here we go. Come over to Doc. Do it just like we did last unit. Insert. Let's put in some data and statistics. There's a bunch of data points. What was the first one? Height. Now come over here. Look at this. And that was weight. Now watch these dots. I hope they're going to make some kind of a liney looking thing where the short people don't weigh as much and the tall people weigh more in general, on average. Let's see. Yeah, I mean, look, it's not perfect, but kind of. It goes up. As you get taller, you tend to weigh more. Okay, so I'm very comfortable calling this linear-ish. I don't know if that's a word, but it should be. So our correlation coefficient was 0.75, which I said was pretty strong. It's pretty gosh darn linear, and it's definitely positive. Think of the slope of a line you might draw in here. Definitely positive. So that's the 3 descriptors for this particular data set. Okay, so that was heights and weights. Real quick, because I want to wrap this up. Let's see, find the following information. We found the mean, found the deviation, found the mean, found the deviation, found the R. We talked about all those things. Okay, I want to wrap this up kind of quickly. So we're going to do one more example very fast, which is this one. Examine the table below. Comment on the strength of the linear relationship between the 2 variables. So I have time and height. And so again, I put these in my calculator for you because I'm nice. I am nice most of the time. Let me come over here. Let's see. What do I have? Times and heights. There we are. All right. So you're going to have to trust me. They're all plugged in. Move picture. Let's do another calculation. Menu, statistics, stat calculations. We have 2 variables. The first one is called time. And the second one's called HT. I couldn't use height again because it was the same thing. I'm going to put the results in column D because that's what I like to do. All right. So here we are. Average height. Nope. Just kidding. Average time. Deviation. Average height. Deviation. I'm looking for R. R is my new interesting letter friend today. Huh. Negative. So my interpretation may be that as time goes on, as time gets higher, the height tends to decrease. Is that true? As time goes up, let's see, I went from 0 to 1. My table's weird, to 2 to 3. So I went from 40 to 54 to 64 to 70. The height seems to be getting higher. So this is confusing to me. I'm not sure what this negative correlation means. Here's why. You should always plot your variables before you talk about the correlation coefficient. Otherwise, you could just be a bumbling idiot. So let's do that. Data and statistics. First one's time. Now watch this. We want it, remember, we want it to be linear-ish. Let's see if it is. That's not linear-ish, no. So this one, there's definitely a relationship, right? Looks to be perhaps parabolic. Maybe there's a quadratic something or other going on here. I don't know, but I certainly know that I'm not going to use R. I'm not going to use my correlation coefficient to talk about this problem because we don't have a linear relationship. We do have quantitative variables, time and height, but they don't have a linear relationship. So do not talk about correlation with a problem like this. Okay, that's as far as I wanted to get, just for an intro, just so you guys have a little background. I think that should be good for a start. We're gonna stop